All right, so in this lesson, we're going to look at the concept of power and kind of define what power means and how power can be used in a context of a problem. So the definition of power is the rate at which work is done over time. A lot of times when we talk about power, we're talking about the rate at which either energy is being absorbed or given off by a system over a unit of time. Things like electrical power, talking about how much energy is being used by, say, a light over, say, an hour, or what is the energy usage of that light per time. A term that you might hear is the term horsepower, used a lot when we talk about engines. How much power can this engine generate, or what is the rate at which energy can be used by this engine? So really what power is the rate at which work can be done or is done over a given time frame. So change in energy divided by time, or work divided by time. So the units of power, we use the units of watts, which is a joule per second. If you ever hear the term horsepower, which is a pretty common term, 1 horsepower is defined as 745.7 watts. So if you had something like a 100 horsepower motor, that horsepower motor is going to be able to generate, or that 100 horsepower motor will be able to generate 100 times this amount of energy, or 74,570 watts. So let's do a couple of quick example problems. Let's say we have a car starting from rest and it accelerates in the x direction, has a mass of 1,000 kilograms, maintains a constant acceleration of 4.6 meters per second squared for 5 seconds, and assume a single horizontal force accelerates the vehicle. Determine the average power generated by this force. So here are the norm pieces of information. We know V0, we know A, we know time, we know mass. The things that I don't know are final velocity, the distance the car traveled, force acting on the car, net force acting on the car, and the power generated by the car. It happens to work out that if we're calculating power, what I need to know is the work done on the car divided by the time it took for the car to do such an acceleration. Work can be defined as force times distance. And so I can rewrite this as force times distance divided by time. Well, distance divided by time, there's a couple different relationships I could use. I could calculate the force by doing mass times acceleration, and I can calculate the distance by doing acceleration, or initial velocity times time, plus 1/2 acceleration times time. If I plug in those two expressions, F becomes ma, x really becomes 1/2 at squared, and the reason because 1/2 at squared is because v initial is 0, and I can do some algebra to solve this out. One of the t's on the top cancels because it gets divided, the two accelerations cancel. So I really get in this problem 1/2 mass times the acceleration squared times t is equal to the power. Now it's worth pointing out that this particular equation may not always work for power. This would be a situation where you know the mass, you know we have a constant acceleration, we know the initial velocity is 0. So this is a really specific or situational dependent equation. Other ways I could go about this would be to use kinematics to calculate x, plug it in, F equals ma to calculate F, plug it in, divide it by the t, and I could work it out that way. So if I plug in all my values, what I get is that the average power is 5.2 or 5.82 times 10 to the 4th watts is the average power generated by this force. Basically, how much energy does this force apply on this car, or how much work does this force apply on this car for every second of time that force was acting on the car? The second problem that I have is an electricity problem. And I looked up the cost of electricity in Faribault, and it's about 5 cents per kilowatt hour. Now, the weird thing about electricity is that we charge electricity based upon the amount of energy you use. The weird thing about the amount of energy you use in terms of electricity is we have this strange unit of kilowatt hours for the amount of energy used. We don't calculate amount of energy used in joules. A kilowatt hour is 1,000 watt hours. A watt hour is a watt times an hour. So we're going to determine the cost of using LED bulbs versus the cost of using compact fluorescent bulbs for 8 hours a day for 5 years, using the information in the table below. And where I've gotten this information is from a common supplier of home goods or hardware. I think I got this from either Home Depot or Lowe's, their website. What is the average LED light bulb, compact fluorescent bulb? What is the power usage, and what is the average lifespan? So one thing to point out is that in 5 years, if we have 365 days in 1 year, and it's worth pointing out in at least one of these years we had 366 days, because there has to be a leap year in there, and 8 hours a day, that means that we've used the light bulb for about 14,600 hours. A kilowatt hour is equal to 1 kilowatt of energy used times an hour. So what we want to do is figure out, well, basically how much does each of the light bulbs cost just to use. So on the left I have the LED bulb, 9.5 watts of power used times 14,600 hours would give me the number of watt hours. Well, I want to know kilowatt hours, so I need to do a unit conversion, watts to kilowatts, which is this third step of the equation. And then I know it costs 5 cents for every kilowatt hours. So in terms of just electrical usage, the LED bulb cost me $6.94. The compact fluorescent bulb cost me $10.22. So 14 watts times 14,600 hours, convert the watts to kilowatts, multiply by the 5 cents per kilowatt hour. Now that's only part of the equation. If I'm just looking at energy usage, the LED bulb is definitely better. But I'm not looking at energy usage, I have to buy the light bulb too. So in terms of buying the light bulb, the LED bulb cost me $9.47 to buy. I need one of them to run it for 14,600 hours. So that means the total cost of using the LED light bulb in this case is $16.41. If I do the compact fluorescent bulb, if it has a lifespan of 10,000 hours, I have to buy 2 of them. The reason why I have to buy 2 is that, well, one is going to last about 10,000 hours. The second one will need to last the other 4,600 hours. So that means that I spend about $14.20 on my compact fluorescent. So in this particular example, the compact fluorescent is slightly better. Now, there's probably a break-even point in here somewhere. If I can continue to run the LED light bulb, and let's say we run it for 22,000 hours, and I add another $1.99 on here, what you can see is I'm already getting close to what the LED light bulb is. So it's possible in the long term that the LED light bulb does work out to be better. Maybe somewhere in the 20 to 25,000 hour usage range, the LED light bulb is better. So this is an example of a problem where maybe under some scenarios this is your better choice, the cheaper light bulb that's less energy efficient, but in other scenarios the more expensive light bulb that's more energy efficient is the better example. We could work an additional problem and maybe try on your own and work an additional problem and try to figure out, is there some number of hours where the LED light bulb becomes better? And it may happen before 20,000 hours that the cost of just running this light bulb more hours, or the fact that it's almost 5 watts more energy, means that at some point you're going to run this cost high enough that it makes up for the difference in cost of light bulbs. So this is kind of a real-world example problem. If you had a scenario, how would you use this energy to begin to calculate? At least in the scenario we have here, this looks like the better option. Like I said, there may be scenarios where that's the better option. So that's kind of a couple quick example problems with power and how we could use power to do, well, a couple of quick calculations.